Hello all, my name is Raghavendra Anand. I'm a research scholar. I am from Electronics and Communication branch from Jain University, Bangalore, India. My proposed work is on about the hardware-based efficient Mickey-128 stream cipher with unrolling factors for the throughput enhancement. So these are the topics which I'll be talking briefly about. The first is about the introduction. Second is about the literature review. And the third is about the proposed design. And then I'll be talking about the result, conclusion, and then the last is references. Coming to introduction, as we all know that nowadays there is increase in the demand for the low resource devices. These devices operate in an environment where like the resources such as energy, memory, power are limited. This IoT application has to operate on these devices. At the same time, it has to protect the data generated from these devices. So the employment of stream ciphers in a Wi-Fi, Bluetooth and other wireless network shows the structure to the mobile communication. The stream ciphers primarily benefit the simplicity of the architecture, as well as at the same time it reduces the mistake in the transmission. Stream ciphers can be coded into software as well as the application specific integrated circuits or else field programmable arrays. So there are two types of ciphers. One is a block ciphers and the other one is a stream ciphers, which are anticipated to to provide privacy and safety and function effectively in the embedded system. Since block ciphers have well-established safety features as well as a simple architecture, they're most popular option on lightweight cryptography. Additionally, stream ciphers are used to establish very improved communication technique when we talk about the streaming applications. Mickey is designed for the hardware architecture with the limited resources. Its main goal is to offer an exceptional level of protection with a minimum of hardware complications. Uh, this is about the literature review. To go ahead with the proposed work, have done a few work on the existing ciphers. There are three stream portfolio ciphers, that is Grain, Mickey, and Trivium, and two stream ciphers algorithm that is Plantlet and the Lizard are presented by Lee et and others. They focused on area usage, efficiency, as well as throughput among the other parameters for comparing these approaches and those found in the available research. And other is like Silva et others. They focused on more significant power evaluation assaults on modern hardware stream encryption algorithms, including Mickey, Grain, and Trivium. And Chen et al., that is the others, that group presented a robust restricted encryption approach to increase the resilience of video security. The suggested strategy is coordinated with the slices. As a result, it facilitates virtual communication and usually decodes it. A packet is lost. And other is a Caband at others. They focused on enhanced Chacha 20 stream ciphers, which uses additional rotation XOR operation with the six rotating constants in order to increase the throughput as well as the area efficiency. And the last is Lee et and others. They made use of a ciphertext which only focused about attack against the geostationary equatorial orbit for the mobile radio interference system. This is the proposed design of the hardware architecture of the Mickey-128 Cipher. It consists of three blocks. One is a finite state machine controller, and the other one is a clock RS generator, and third is about the RS mapping unit. The Mickey-128 primary function is to withstand targeted attacks while maintaining a randomness. It achieves this by unique hardware, which is crucial in generating a random clock cycling. This hardware make use of 128-bit initialization vector, 128-bit key size, as well as this FSM control is a main component of the encryption process. This encryption relies on the 128-bit R and S register, where R act as a linear and S act as a nonlinear register denoted by R naught to R127 and S naught to S127 respectively. That RS clocking unit is individually represented in this architecture. It consists of a RS input generator, R clocking and S clocking unit, which includes R tapping and R generator component, as well as S component and S generator component. The FSM controller is main in configuring the key initialization vector and the key stream generation. Using it, make use of a two clock registers, the clock R and S generator, which is used to produce a pseudo-random characteristic based on the clocking. This R clocking unit in the Mickey-128 stream cipher is responsible for generating uh, R generation for R taps. That is mentioned the equation one. For CR stands for the uh, R clocking and CS stands for the S clocking bit. This clocking R bit is obtained by performing XOR operation on the S43rd as well as R85th bit, and S bit clocking is obtained by doing XOR operation with the S85th bit and R42nd bit. Similarly, FR and FS are the feedback signal for the R and S clock generator. The FR is obtained by performing an XOR operation with R127 as well as D in signal, and FS is obtained by performing an XOR operation with S127 and D in bit respectively. To determine the range of R's feedback, we make use of a tap places, each R tap location to perform the XOR operation and to apply a feedback bit FR, which is obtained at these tap positions starting from 0 to 126 bit. These R tap positions are generated randomly, and the R generation unit only uses the most recent R tap result as the last R clocking R out when the done signal is activated. So S clocking procedure include S generation as well as the S component parts. The S component performs the XOR calculations using a 128-bit component 0 as well as a component 1 variables after receiving the S in input from the RS input generator. To define the parameters for the component 0 and the component 1, we make use of the equation 4. The component 0 is of 127-bit and the component 1 is of 127-bit. Following obtaining the S component outcome, that will be fed as an input to the S generation to create the S clocking output. Using the feedback bit FS and the 128-bit feedback elements, which is represented by FB0 and FB1, which is defined as a 127-bit in the equation 5. FB0 and FB1 is defined in the equation 5. This is the algorithm for the Mickey-128 stream cipher. Here we'll be defining the input 128-bit key as well as initialization vector and the output as KS0 and the KS valid. We'll define the control input signal as D in and the mix signal, which is generated using a finite state machine. For the clock RS generator, control bit generator CR and CS are already defined the equation. Similarly, the feedback bit generation FR and FS for R taps are also defined in the equation 2. Here, the input RS input will define if the mix is 0, then Rin is the actual the original D in value. Else, it has to be XORed with the S64th bit. Similarly, S in is equals to D in for all n belongs to greater than 1 and less than 127. For R clocking, R out equals to 0 and R out is equals to R in minus 1, whereas N, which belongs to greater than 1 and less than 127. For R tapping, N belongs to R taps, then R out is equals to R out N, that has to be XORed with FR. Similarly, for the control bit 0, then R out is equals to Rn, else it has to be XORed with the Rn, whereas N belongs to greater than 1 and less than 127. Similarly, for the S clocking, SC0 is 0 and S1 to SC127 is equals to the most recent output S126. SCN is equals to SCN minus 1, that has to be XORed with SCN plus component 0, 1 and SN plus 1 that has to be XORed with component 1 n for all n greater than 1 and less than 126. If control bit equals to 0, S out is equal to SCN, else S out is equals to SCN that has to be XORed with FBN FS, whereas n greater than 1 and less than 127. For the RS mapping, R is equals to R out and S equals to S out, whereas n greater than 0 and less than 127. And the FSM controller, we define it as KS0, KS valid equals to finite state machine key, initialization vector R and S. This is the overall hardware architecture of the proposed Mickey-128 Cipher with unrolling features. The design includes an RS mapping unit with N times as an FSM controller and a clock RS generator. N stands for the unrolling factor or the unrolling feature. A Mickey-128 cipher with n equals to 1, 2, 4, 8, and 16 is employed in the present study. Handling the R and S output of the RS mapping unit continuously complete the unrolling procedure. For each n unrolling factor, the design modifies the control signal CR and CS and intermediary outcomes R out and S out n minus 1 times. One way to reduce the key, that is key and initialization vector strategy, is to divide the clock cycles, that is 256 clock cycles, by an unrolling factor. It might be 1, 2, 4, 8, or a 16. This makes this method effectually for increasing the throughput. This figure shows, figure 4 shows the simulation results. The clock, sorry, the clock is enabled and reset is made high and low. Then we'll define the key of 128-bit and the initialization vector 128-bit. And once the valid signal goes high, it takes 256 clock cycles to initialize both the 128-bit initialization vector and the key. Once the valid signal goes high, it produces the 128-bit output. And the table shows the resource usage of the Mickey-128 cipher on RTX 7 hardware. You can see that it makes use of 204 slices and 268 lookup tables, and it operates at a maximum frequency of 639.1 megahertz, and the power usage is about 88 milliwatt, whereas dynamic power is about 6 and the rest is about a static. And this is the resource usage of Mickey-128 cipher with unrolling features. It's starting from 1 till 16, that is 2, 4, 8, and 16. You can see like the lookup tables in the unrolling factor is 268, whereas in 4, 8, and 16 is less than 1% or equal to 1, and it operates at the maximum frequency of 639 megahertz, and the total power is about 88 in the one unrolling factor, and it keeps increasing at 2, 4, and 16, and finally at the 16th unrolling factor, the total power is about 184. And in the figure 5 shows the representation of the chip area usage of Mickey-128 with unrolling features. You can see that as the unrolling factor increases, the lookup tables are also reduced comparing to previous unrolling factors. And the table 3 shows the throughput analysis of the Mickey-128 on various FPGAs. We have compared with the Spartan 6, Vertex 7, and RTX 7. For the unrolling factors, the Spartan 6 is about 0.327, whereas for unrolling factor 16 is about 5.23 megahertz. And figure 6 shows the representation of the throughput analysis of Mickey-128 on various FPGAs. We can see that for Spartan 6 to Vertex 7, the Spartan 6 shows the lower throughput, whereas the Vertex 7 shows the higher throughput for the 16th unrolling factor comparing to the previous unrolling factors. These are the resource comparison of the proposed Mickey-128 with existing Mickey-128 ciphers. The existing were about Vertex 2, Spartan 3, and Spartan 6. Here in this work, we have made use of a Spartan 6 FPGA, which consumed 203 area slices and operating at 327 megahertz, and efficiency is about 1.67. So compared to other FPGAs, the Spartan 6 works at a higher throughput, shows the higher throughput compared to previous FPGAs, that is other FPGAs, Vertex and Spartan 3. Coming to conclusion, this manuscript described the design and implementation of the Mickey-128 stream ciphers. A mapping unit, FSM control, and the two clock register R and S are used in the construction of the Mickey-128 cipher. The Mickey-128 cipher uses the unrolling function as an optimization technique to increase the system throughput while requiring minimum additional resources. The suggested Mickey-128 cipher runs at a 639.1 megahertz on Arctic 7 FPGA with a power consumption of 88 milliwatt and a chip area of less than 1%. Employing an unrolling factor up to 16, the Mickey-128 cipher runs at 10.23 gigabits per second with an efficiency of 3.18 megabit per second slices. The efficiency, throughput, and frequency matrices of proposed Mickey-128 cipher are compared to those of the existing Mickey-128 ciphers. Security analysis about the anticipated Mickey-120 ciphers assaults will be assessed in the future. These are the references which I have referred for this proposed work. Thank you.